Welcome everyone. Thank you for joining today's webinar on the energy savings from NLCs with and without LLLC. I'm Bhagwat Mohan. I'm the Senior Technical Operations Analyst at the DLC for the Network Lighting Controls program. I manage the qualified products list used by our member utilities to determine system eligibility for their energy efficiency program incentives. Joining me today are two lighting experts, Yao Zhang Wen and Chris Walgamot. Dr. Yao is a senior engineer at Energy Solutions, where he leads technical research on energy and non-energy benefits of connected devices and systems, including network lighting controls. Yao has provided technical support on several DLC policies over the past few years. He has previously worked as a senior research scientist at a major lighting company, where he focused on advanced lighting control technologies and was involved in several lighting system standardization activities. Chris Walgamot has worked in the utility business in the Pacific Northwest for over 23 years as a program manager, energy efficiency engineer, and product manager. Mr. Walgamot is recognized as a subject matter expert for luminaire level lighting controls. His work in the utility business has allowed him to gain vast knowledge on how incentive programs are developed and run. As the senior product manager for commercial and residential lighting with NIA, Chris leads all emerging tech research on lighting products to support transformation of the commercial and residential lighting markets. He works extensively with lighting manufacturers on where the future of lightings and controls are headed. So here is the brief agenda for today. I will be giving the introduction, followed by Yao, who will present the methodology for savings calculation and results. And based on the results, I will outline the findings and recommendations inferred from the study for improving methods for energy data collection and reporting. After that, Chris will share his thoughts on utilities' perspective on the study's findings and how the Northwest utilities will use this data in their efficiency programs. We will wrap up the session with a Q&A. Webinar logistics. We have a large audience today, so everyone will be on mute through the duration of the webinar. We do encourage you to support and submit questions to us using the questions pane. If you face any technical issues, please use the chat feature to let us know. We are monitoring that closely. The webinar is being recorded and will be available in the DLC website. Before we begin, we would like to express our sincere thanks to all the organizations for their support and perseverance through the various challenges to contribute for this project. From the results of this study, we see the significant potential of network lighting controls to deliver savings above and beyond savings from LED lighting. With the rapid growth of IoT technology in the recent years, NLCs can now talk BACnet and other protocols to interface with BMS and HVAC to even offer benefits beyond energy savings, such as user comfort, operational efficiencies, security, and other value-added services such as the ones shown here. This ties in with the interoperability report for NLCs published by the DLC in May, in which 3 critical use cases were identified and explored in depth: the barriers, opportunities, and value propositions for various stakeholder groups, and how they can work together to accelerate the market adoption of NLCs and capture the untapped energy savings. This report builds upon the 2017 study published by the DLC. So what's new this time? This study utilized all of the 2017 data and expanded the project sample size, more manufacturer diversity with an increased representation of NLC systems with LLLC, added data sets from healthcare sites. There is also a separate analysis of HighEnd Trim versus other control strategies, and as the title goes, a separate analysis of LLLC effect. We are excited to announce that the results of this study are consistent with the 2017 study findings. The average energy savings across all buildings is 49%, which is an overall 2% increase. The highest savings were found in offices, warehouses, and manufacturing facilities. Among all the control strategies available, HighEnd Trim contributed the most to the savings. Now I'll flip over the control to Yao to explain the methodology and results.
Thanks, Bhagwat.
Yeah, we should have
if I have control. Yep, great. So let's first look at our outreach and data collection methodology. When we started to collect more recent NLC energy data, it was around the time when the California Consumer Privacy Act was about to take effect. So we actually first researched the CCPA as well as European's General Data Protection Regulation, or GDPR, to make sure we were not running the risk of violating the regulations. So after that, we first contacted 38 organizations which we thought were likely to have access to NLC energy data. These organizations included manufacturers, utilities, research organizations, and a few end users. And at each stage of the conversation, we tried to get from our initial contact to the right person within the organization, assess their willingness of participating in this study, determine if they were in possession of or had access to NLC energy data, and finally make sure the kind of data they had was what we needed for the study. In the end, we received data from 8 contributors. So the main challenges we faced were lack of access to data, including physical difficulty of downloading data from the installed systems and difficulty of gaining authorization to download and share data with us. But most often, the challenge was simply lack of data because the installation were too new, energy reporting was not activated in the system, or the format of the data was not what we needed for this study. So here's a high-level summary of the data we collected. This includes the data collected and used in the 2017 NLC savings study Bagua mentioned before. So not accounting for the data we had to discard due to quality issues, we included NLC energy data from 194 buildings across 8 building types and 12 manufacturers. And as you can see, we had the highest number of data sets for manufacturing facilities, followed by office buildings. We also had a good number of data sets for educational facilities. We had hoped for a much stronger representation of warehouses and healthcare facilities, both in terms of the number of data sets and diversity in manufacturers. But unfortunately, the data was just hard to come by. And this is probably something for future improvement. More details about the data. The average duration of the data sets was 9 weeks, with the longest being more than 2 years and the shortest being 12 days. Most data sets we collected were interval data. And while we had the highest number of data sets with the reporting interval of 15 minutes, 5-minute and hourly reporting intervals were also quite common. In addition, about a quarter of the data sets were event-based, which means data was recorded when a light level change occurred due to, for example, occupancy sensing or daylight dimming. Lastly, during the study, we made an effort to collect energy data from NLCs both with and without luminaire level lighting controls, or LLLCs. So overall, we had almost an even spread between NLCs with and without LLLC across all 194 data sets. However, I wanted to caution that this does not mean there was the same even spread for each building type. Okay, so let's keep this in mind when looking at savings analysis in the later slides. So in terms of the geographic location of the NLC installations, all of them were in North America across 35 states in the United States and 5 provinces in Canada. In addition, there were also 10 installations in Mexico. Across newly collected data from 8 contributors, we had 9 unique data formats and 18 subformats. So a subformat is just a derivative of a unique format with only slight differences. So for each data format, we had to develop a script to extract the time series energy data from whatever form it was provided to us, clean it up and load it into the database. And After processing the data, each data set has two components, time series data and static attributes. The time series data is the NLC energy data. The energy could be reported per fixture, per zone, or even per building, depending on the raw data provided to us. And the static attributes are fixed information related to NLC installation, such as the geographic location we've just seen, or the gross floor area, or the rated power of the luminaires controlled by the NLCs, etc. So from the time series data and static attributes, we were able to construct baselines and calculate savings against the baseline. Now let's move into the discussion of how energy savings were calculated. Energy savings in this study is estimated against the baseline with LED luminaires, but without controls. So let me explain this here. In a typical savings calculation, it will start with the incumbent lighting system with traditional light sources, such as linear fluorescent, HID, etc. And when the traditional light sources are converted to LEDs, assuming no other controls are implemented, the difference would be the savings from LED conversion. Let's say we go from 100-watt luminaires to 60-watt LED luminaires. Then the savings would have been 40 watt per luminaire, or 40%. Now, when we implement a combination of control strategies using NLCs, such as HighEnd Trim, occupancy sensing, daylight harvesting, so on and so forth, we further reduce the energy consumption of the LED luminaires. And such reduction is the savings from controls only, with LED lighting as the baseline. And this is the number we are trying to capture in this study. Now, for a typical NLC retrofit project to calculate the overall savings, it will be the cumulative savings from both LED conversion and controls. Again, since this study focuses solely on savings from NLCs, all the values reported in this study represent savings of installing NLC system with existing LED luminaire, irrespective of the pre-retrofit lighting installation. So to calculate savings, we need a baseline. The data we collected are mostly from actual projects where the controls were in effect from day one, right? So most data sets do not contain information about the pre-NLC energy consumption, nor do they report a post-NLC baseline energy consumption where the controls were deliberately disabled. So for the baseline, we adopted the inferred baseline method developed as part of the 2017 NLC savings study. The inferred baseline is constructed from the normalized hourly NLC energy measurements, the gray area in this illustration, and therefore is specific to each data set. And to obtain the inferred baseline, we first calculate an occupied threshold, which essentially is defined as 10% of the maximum measured power after the base load is removed. And the base load is the load consistently present in the measurement due to, for example, egress lighting. Now, once we have the occupied threshold, if the normalized measurements are above the occupied threshold, which we designated as the occupied hours, then the baseline is assumed to be the rated power. And recall that rated luminaire power is one of the static attributes in the NLC datasets. Conversely, if the normalized measurements are below the occupied threshold, i.e. the unoccupied hours, then the baseline is assumed to be equal to the normalized measurements. In other words, no savings are assessed in this case. And the difference between the inferred baseline and the normalized hourly NLC energy measurements, the light green area in the illustration here, is the savings attributable to NLC systems. And we realized that there are other baselining methods and techniques. And the main reason we adopted the inferred baseline method was because it is consistent with the methodology used in the 2017 LLC savings study. So one can directly compare the results reported in this study with those in the previous 2017 study. And of course, in addition, this method is unobtrusive and inexpensive, scalable and reproducible. It is project specific and can be highly granular. And it also has been reviewed by NLC and EMNV experts as part of the 2017 study. There are inevitably caveats using the inferred baseline method, just like using all other baselining methods. So specific to inferred baseline method, the first caveat is that it assumes full lighting power during occupied hours, thereby not accounting for any pre-existing controls. And this would be a source of overestimating the actual savings. Secondly, the occupied threshold mentioned in the previous slide implicitly assumes the existence of some sort of basic scheduling control in the baseline, and therefore not counting any energy savings during non-occupied hours. And this will likely to have resulted in some level of underestimates of the actual savings. Now we have looked at how the overall savings for each data set is calculated using the inferred baseline methodology. In this study, we also tried to further dissect the savings and attribute them to different control strategies. So continue the same illustration from the previous slide. The green areas with blue stripes are the areas between the rated power or the maximum luminaire output and the highest output observed in the actual time series energy data. They are most likely savings exclusively due to HighEnd Trim. And the rest of the savings represented by the green areas with orange stripes would be the contribution of all other control strategies combined. And we will separately look at these two savings in one of the later slides. But one important thing to note is that the savings by control strategies other than HighEnd Trim in this study is calculated against the inferred baseline with the savings from HighEnd Trim removed. This allows us to better reflect their savings potential free from the built-in influence of HighEnd Trim savings in the inferred baseline. And we will touch on this a little bit more later on. So let's look at highlights of the results. As we have seen at the beginning of the webinar, the average control factor is 0.49 across all 194 NLC energy data sets included in this study. Here, we use control factor and savings interchangeably. When referred to as control factor, it is a number between 0 and 1, representing the fraction of energy saved. And when referred to as savings, it is simply the percentage of the control factor. So in other words, the average control factor of 0.49 is equivalent to saying 49% savings. And this chart also shows that savings for each individual building vary significantly across the board, from 2% all the way to 91%. And as Bhagwan mentioned before, the highest savings are found in offices, warehouses, and manufacturing facilities. And before I go into the next slide, just a heads up that this same plot will appear repeatedly throughout the rest of the webinar, but with different color coding as we look at various aspects of the savings analysis. So this box and whisker plot shows the distribution of NLC savings for each building type. Each box and whisker represent a different building type, and the green circles within represent savings of each individual buildings of that particular building type. So in all the data we collected, assembly buildings have the lowest average savings of 28%. And the average savings is the highest for warehouses, which is 68%, followed by 64% for office buildings. And regardless, savings vary significantly within each building type. And this is the same observation that has already been made in the 2017 study. As explained in the previous slide, we tried to attribute savings from HighEnd Trim and other control strategies separately. And this chart shows the composition of the two sources of savings for each building. The blue portion of each bar represents savings from HighEnd Trim for the building. And the orange portion of the bar represents savings from other control strategies. And as we can see, in most buildings, HighEnd Trim contributed to significant savings compared to other control strategies. And as noted before, offices, warehouses, manufacturing facilities have the highest savings. And this is largely due to very aggressive HighEnd Trim. On average, HighEnd Trim contributed to 27% savings across all buildings. And all other control strategies combined, the orange part, resulted in an average savings of 32% across all buildings. And again, recall that this number is calculated against the inferred baseline with savings from HighEnd Trim removed. So the savings would have been 22% for all other control strategies if it is calculated against the inferred baseline without removing the savings from HighEnd Trim. Now let's zoom in on the savings from these other control strategies across the 194 buildings, i.e. only the orange part of the previous chart, except now we sort the chart by the amount of energy saved and color-coded by building types. So there doesn't seem to be a particular building type with consistently high or consistently low savings. In other words, the savings opportunity from other control strategies is likely to be dependent more on each building and NLC installation and commissioning than on building types. So buildings with high savings are likely the result of a combination of, say, implementing multiple control strategies, aggressive control settings, such as shorter occupancy shut-off time delay, or maybe beneficial site characteristics, for example, ample and deep penetration of daylight, and maybe occupancy and space usage patterns and user behaviors. Now, taking the advantage of the even split between NLCs with and without luminaire level lighting controls, we can look at the savings potential for LLLCs. So going back to the overall savings chart we've seen several times throughout this webinar, and this time it is color-coded by whether or not the NLC system is an LLLC. From the collected data sets, LLLCs dominated the high savings spectrum with an average savings of 63%. And while not explicit in this chart, we also found that offices, warehouses, and manufacturing facilities are the building types where LLLCs are most prominent. And LLLCs seem to be a lot more aggressive, producing savings from HighEnd Trim. And of course, I should caveat these results by pointing out that while we have an overall evenly spread data sets between LLCs with and without LLLC, we do not have such even spread within each building type. And since LLLCs are most prominent in offices, warehouses, and manufacturing building types, the average savings here are inevitably skewed towards those building types. So the analysis can be further improved in the future by having more comparable numbers of data sets of NLCs with and without LLLC within each building type, and having more diverse representations of NLC manufacturers, both with and without LLLC. So here are some highlights of the results. I'll hand this over back to Bagua to discuss findings and recommendations.
Thanks, Yao. So there is significant opportunity to build on the study from the savings estimate that Yao just presented. And in this section, we will explore some key findings and recommendations for utilities and energy efficiency program administrators on some next steps to explore incentives offered for NLCs. The average energy savings across all buildings in the study was 49%. However, site-specific variation is a much larger driver of energy savings than general factors such as building type. Some sites appear to implement aggressive HighEnd Trim and optimize their control strategies to achieve deep savings, while others may be using the systems in a more basic manner. Visual analysis of load profiles during the quality control process suggested that many sites with lower savings are simply using NLC as a zone-level scheduling control with HighEnd Trim and not implementing the other control strategies. There is likely significant differentiation in occupancy timeouts or settings such as auto on versus manual on. And other major factors that impact the energy savings is the amount of available daylight, occupancy patterns, and individual users' tendencies to turn off the lights when not present. Recommendation: efficiency programs are able to use 49% as the best estimate of average portfolio level energy savings for their efficiency programs. Because the buildings included in the study were not identified through a random sample, it is also not possible to definitively determine if the 2% gain in the savings estimate is due to increased familiarity with the technology and improved commissioning. However, 49% represents the average savings from NLC systems across 12 manufacturers, 8 building types, and 194 buildings, and is therefore the best available estimate of average NLC performance. Energy savings from NLCs vary widely by individual site, and thus energy efficiency program administrators should treat this 49% figure as a best estimate of what a portfolio of projects might achieve, rather than an individual building. NLC systems with LLLC showed overall higher savings than systems without LLLC. As you can see from this table below, LLLC can save up to twice as much energy as systems without LLLC. While this implies that control strategies implemented at the luminaire level may yield higher savings, it cannot be inferred at this time that LLLC is universally superior in all applications and building types. A larger study including more diverse NLC systems with LLLC controlling for potentially confounding variables is still needed to confirm the study at a portfolio level. It may be worthwhile for utilities to explore new program designs and incentive structures around LLLC to capture greater savings. Further studies still needed to create more robust savings estimates for NLCs with LLLC at the portfolio level and for each building types. In this section, we will explore additional findings and recommendations to inform the NLC industry and the utilities on some next steps and action items to standardize the energy data to further the market penetration of network lighting controls. As Yao mentioned, during the outreach and data collection period of this study, it became evident that each manufacturer had varied knowledge on the details of the NLC installations and ability to share the data due to different sales models. In some cases, manufacturers had the data centrally managed in the cloud, while some store it locally within the system. The other scenario is where they had contractual agreement with customers to access the data, or they reach out to the customer on a case-by-case basis. Energy efficiency programs should be the primary drivers for collecting NLC energy data as part of their programs, as they have the direct engagement with program participants in all cases. As you can see from this screenshot of the NLC QPL, 47 out of 51 systems listed have energy monitoring capability. With this capability becoming ubiquitous in NLCs, program administrators must strongly consider making energy reporting a requirement for NLC incentives. And this collected data must be actively used to evaluate savings on a per project basis. Energy efficiency programs for NLCs should consider including clauses in their customer participation agreements that authorize the sharing of anonymized data. The NLC data comprises of two parts, the static attributes and the time series data. For energy data directly reported by NLCs as opposed to separate data loggers, the time series data is the direct export from the NLCs. The static attributes such as the post-NLC rated power, on the other hand, were typically provided in a separate document during the data collection period, which is more susceptible to human data entry and transcribing error. Some NLCs may be able to export static attributes, but they are only as accurate as the information manually entered at the time of commissioning. Whether or not the NLC energy data is collected as part of the efficiency program, the static attributes need to be carefully verified by the data collector for accuracy. This is critical in ensuring the accuracy and quality of estimated savings for each project. The essential static attributes vary based on the intended use of the energy data. For instance, if an efficiency program intends to evaluate the energy performance using metrics such as lighting power density, then the gross building area of the NLC installation would be an essential static attribute. From the utility perspective, the best time to accurately collect these static attributes is at the completion of the NLC installation. The size of NLC energy data grows rapidly as the spatial and temporal granularities increase. For instance, a data set reported at the building level for 2 weeks at 15-minute intervals could be as small as few hundred kilobytes, and in contrast, a data set at the fixture level for 6 months at a 5-minute interval could easily be several gigabytes. Even in this study, this discouraged some contributors to provide the most granular data. This suggests that it would not be a scalable model for efficiency programs to require the most granular energy data. The NLC program administrators should standardize the energy data reporting format and requirements to facilitate program participation and streamline the process. When considering the performance metrics and evaluation methodology, the key is to strike a balance between accuracy and scalability. While energy data with the highest granularity and longest duration may result in the most accurate representation of the actual performance, the large size of the data files will make data intake, processing, and analysis really challenging and unscalable for efficiency programs. It is critical that efficiency programs specify and standardize the spatial and temporal granularity and duration requirements. The DLC is working with NEMA C137 Lighting Systems Committee in developing an energy reporting standard for network lighting controls and is in full support of the ongoing efforts. Moving on to the final finding. The average inferred occupied hours for buildings in this study are substantially longer than the average deemed operating hours assumed by many utilities and efficiency programs throughout the US in their technical reference manuals, also known as TRMs. This large discrepancy between the inferred hours and deemed operating hours may result in lower overall savings for projects using deemed operating hours. This study and any future updates to the study could serve as additional data points for the TRMs to calibrate the deemed operating hours. And now I'll pass control over to Chris to talk about the utilities perspective on this study and how efficiency programs can utilize this data.
Great, thank you, Bhagwan. I'm going to, I think, figure out how to move. There we go. So I'm just going to talk about a little bit. A lot of the stuff that we're going to talk about is the same stuff that we've already hit on in what the Northwest is going to look at. Specifically, NIA is going to look at and how we're going to use this data. For me, when we look at the past study and this study, the biggest sort of thing that jumps out at me for the savings, the average savings across, is that it's pretty darn close, and that that means that the numbers that we've been using in the Northwest are for energy savings for programs are good numbers, and we're seeing proof that we're not exaggerating numbers. We're not outside the realm where these numbers are coming for the programs that are in place right now, which is a great thing. It just shows that we've done a good job, and that the first report was a good report as a starting point. There's a lot of things that in this report that I think build on that last report that help the utilities and our region be able to come up with differences in programs. This slide, you've seen the numbers before, is a big one for us, I think, because it shows the difference between what LLCs offer and what systems that aren't LLCs offer in savings wise. This is one where utilities, I think there's as Bhagwat said before, utilities should be starting to look at, do we separate NLCs into two pots, or do we keep them together? In the Northwest, we have a few utilities that have this separated out, and we have a few utilities that have them as one pot. The big thing when you're looking at it as a single pot is if you're getting more of the NLCs without LLC in your system, in your program, and you're counting that higher number of 49% or 47% and 50%, that you may not be getting that savings out of the program because you might not be seeing that number as we're seeing that the averages are lower. The transverse of that is if you're getting a lot more LLCs, you may be shortchanging yourself a little bit when it comes to the savings numbers because you may be seeing bigger numbers with the LLCs that you're not getting to account for. So it's definitely something that we think in the Northwest we should be looking at them as two separate products, and we have that in our regional technical forum, which has some numbers for LLC, and they're going to be updating their numbers at the end of this year for the year 2021. And in general talks with them at this stage, we're seeing them wanting to up the LLC number and reduce the NLC number that they have in there, which will translate over to the utilities as well. This is you saw this one as well, nothing new here. HighEnd Trim average 27, other controls 32% across the average of all the NLCs, including LLC and NLCs. But what we do see is that when you go to and you break this out with LLC, the average is a little higher, but the HighEnd Trim is higher, but so is the other control savings. So you want to know that, when you're looking at this, that we're seeing much larger numbers on both sides of this, where the savings coming from coin, right? So you're seeing higher HighEnd Trim numbers, but you're also seeing much higher controlled savings with whether it's occupancy or daylighting that are coming from the LLC as well. And I think that the utilities we talk to and how they work, a lot of them don't really account for the HighEnd Trim piece, but we are definitely seeing more HighEnd Trim as we're pushing through this. So, that's one of those things that, here at NEO, we've said for a long time that I think that one of the largest possibilities of energy savings from NLC or LLC is the HighEnd Trim. And if that's done right in the system, there's quite a bit of savings that's there for the utilities to account for and help with their savings numbers. As we see these numbers increase, it could help with your ROIs and what your incentives are, because you're seeing bigger incentives with these numbers through LLC and NLC. So I think that's the end of mine. Mine was really short, and we can get into the questions.
Yeah, thank you, Chris. If you're interested to read the full report, it can be downloaded from the DLC website under the Resources tab. The webinar is also being recorded and will be made available in the website. Now let's check with Emily Kamier at Energy Solutions, who has done a great job in coordinating and managing the overall project over the past year, and also been monitoring the questions today.
Thanks, Bhagwat. Thanks, everyone, all the presenters and everyone for sending questions. Please continue to send questions as we go through these, if anything else comes up. The first one, just real quick, I wanted to confirm that this study is only on indoor lighting systems. All right, next question is, I would assume the assembly savings were lowest from a savings standpoint due to lower operating hours. Can you confirm that assumption is correct?
Yeah, this is Yao. Let me try to answer the question. And as you have seen in one of Bhagwat's last slides, the operating hours, we inferred from the data sets for assembly buildings. It does look like it's significantly lower, but there are a lot of variations within each building types, right? As we have seen in the box and whiskers plot. So there could be a number of reasons that the savings for assembly buildings is lower. For example, assembly buildings, the spaces typically have very highly concentrated occupancy patterns for the event, and after the event, there's not much activities going on there. So perhaps the savings opportunities is a little different from other building type and cause the lower savings figure. And another possibility is also that the number of data sets we have for assembly buildings is relatively low compared to other building types, such as manufacturing facilities or offices. So the savings could, again, be skewed just because a relatively low number of data sets.
Thanks, Yao. There was a question, and I wanted to confirm that this webinar recording will be posted on the DLC website. Bhagwat or Levin, are you able to give any more detail about where that will be found on the website and when attendees can expect that to be posted?
This will be available in this slide that's been shared. It will be in designlights.org under the resources tab. You can find the report and the webinar recording. It should be available next week.
Thanks, Bhagwat. There was an interesting and helpful comment. Someone mentioned that aggressive occupancy controls are not popular with occupants in open areas, and he has found that occupants will accept aggressive controls if instead of off, unoccupied areas go to 5% or 10% when near occupied spaces. Thanks for your input of that experience.
Yeah, let me just add to that. This is we certainly agree that user comfort is the most important driver and the key considerations. So we are not trying to advocate for a very aggressive control settings, especially for occupancy controls. And I also wanted to point out that this is probably most applicable to office building types. And we also have warehouses where savings are the highest. So in that case, it's may still likely to be a relatively aggressive occupancy controls just because of the usage pattern and occupancy or traffic pattern in warehouses.
Thanks, Yao. There's another question that I think it would be great for you to take, Yao, and that is, can you please define HighEnd Trim?
So HighEnd Trim is one of the controls capabilities where during the commissioning or startups process, when you have when the luminaires can have more light output than you want or than the occupant needed or than the design specified, then you can trim it down so that when you use the wall switch or wall dimmer to turn the lights all the way up, it won't go all the way to the full amount of light it can provide. Just turn it up all the way to the amount of light you are allowing the luminaires to produce. And the same concept goes to the interaction with other controls. So in the same sense, when you have occupancy control, when the occupancy sensor is triggered, the light will turn on to the trimmed level instead of the full level. And same goes to daylight harvesting. When you don't have daylight, then it will stay at the trimmed level instead of the full level. And this control typically is implemented during commissioning or startup, and it's not to be confused with personal control, where the person can use the wall switch or dimmer, or in some cases some sort of remote control to manipulate light level, and that is considered to be personal control or personal level control. But high-end trim is determined typically by the designers or by the electrical engineers at the beginning of LLC deployment, the startup and commissioning process.
Thank you. Yeah,
I'm just going to add a little bit to that, in that one of the things that we see is that LEDs tend to be perceived as brighter, so the new systems get put in, and a lot of times that trim, they're lowering that down because it's not that the bad design, they put in the same lumens or whatever, but you do see that being done a lot of times where that trim is brought down because it feels too bright in there for the people. And I also say that there are a few manufacturers out there that are shipping products in this with trim already set in place at a certain level because of that. So we are seeing that already in place, where they're being shipped at that somewhere between 10 and 20% high-end trim already in place from the factory. And you know, just as a note, for most people know this, but the human eye can't usually detect between that up to about 20% difference in the light. So when you lower it 19, 20%, the eye can't tell the difference between that. You know, optometer can, but the eye can't. So a lot of times that's one of the reasons people are trimming it, is they can make it feel less bright, but the people don't know that it's less bright, and the energy savings can be significant.
Thank you, both of you. And I just wanted to reiterate everything you said, and the official DLC definition says that the capability, or high-end trim, is the capability to set the maximum light output to a less than maximum state of an individual or group of luminaires at the time of installation or commissioning. Great question. Let's see. Next, we have, from the other control strategies, is there an idea of what the percentage split is for control strategies that are required by energy code and what would be above code?
Yeah, let me take this one. So unfortunately, that was beyond the scope of this study, and because energy code differ from state to state, so we were not able to, with the data, the type of data that we collected, and both the time series and, most importantly, the static attributes data we collected, there was not enough information for us to discern what portion of it is above code and what portion of it is just to meet code.
Thank you, Yao. All right, another question from the same attendee. What would the expected measure life be for controls that are performing high-end trim? Does anyone have intel on that?
You know, measure life is one of those ones that's sort of a utility-centric thing. I think that when they're built into the fixture, you know, this is my opinion and not anybody, you know, no utilities opinions, that's my opinion. But when you do it like with the LLC version, where you have the fixture and the controls are integrated and it's one system, and you can't really have one without the other, I think the measure life should be longer than the typical 2 to 5 years that utilities give controls, because you can't have one. The fixture is there for 15 years or 12 years or whatever the measure life it is. I will say that with high-end trim, when you do high-end trim, you are underdriving the driver. So the life expectancy should be longer for the product itself. So the fixture should last longer if you're not pushing it as hard because you're only running it at 80% or whatever. The other benefit to high-end trim is if the fixture stays in long enough to where the light lessens because of degradation, you do have the ability to turn that fixture back up to continue to have the same light level. But I don't know, it takes a long time for the light on LEDs to come down to a measurable point where it's going to make a difference. And by that time, you may be changing the fixtures out anyway. So I don't know, but, measure life for the fixtures and the controls should be a longer number with this type of system, specifically LLC, but NLC too. But that basically just comes back. We haven't had them long enough to be able to come up with a good number on what that is, I don't think.
Thank you, Chris. All right, the next question is, based on all of the benefits listed in this webinar, what are the barriers to getting the technology put into buildings? Do contractors not feel comfortable? Do they not know about it? What challenges have been experienced? Can someone at DLC or NIA speak to this one?
Yeah, sure. One of the major barriers that we see is the lack of education on the NLC technology itself. Like especially with the rapid growth in IoT now, the technology is also rapidly growing and changing. We have more wireless gateway controls, and API is being a majorly used platform now for installing and commissioning. So I think lighting designers and contractors need to be more educated and feel confident enough to install a control system in the buildings. And this will also be supported by utilities incentive programs that they come up with for NLC installations. That would definitely play a huge role in the market adoption.
Thanks, Barbara.
I think the other thing to sort of add on to that on the education side, which I think is important on everybody, I think it's also, we're finding in the Northwest where we've been pushing these for a while now, is that the education of the contractor is important, the education of the installers and designers and lighting professionals. But we've come to the conclusion that it's also the lack of knowledge by the building owners and the customer that these products are available. A lot of times they don't know that they're there, and they don't know what they're capable of. And so, that I think is another place where some work needs to be done to sort of break the barrier of getting people the knowledge of getting them installed.
Relevant comment from Liesl at the DLC. Thanks, Liesl. DLC offers network lighting controls trainings through utility members available in both online and virtual hands-on training. Thought that was related to what we were just discussing. Okay, we have another question. Are all these luminaire level lighting controls also networked? What about LLLC without networking?
So let me go ahead.
I was just going to say, and maybe Bhagwat should be the one answering it, but my understanding is if they're not networked, they're not LLC according to the DLC's list. They would be room-based.
I would say, yeah, this is Levin. If the word network in the question refers to connected to the internet, they were actually all connected to the internet because the way we did this study was by collecting data over the internet. So any data that was confined within a single building was not accessible to this study.
Yeah, and the networking capability that we have in our technical requirements refers to the networking between luminaires and controllers and sensors.
Did you want to add anything, Yao, or did that cover it all?
Yeah, I can just add a little bit more on the data collection side. So I can confirm from here that all the NLCs with luminaire level lighting controls included in this study, they are all networked and they are all on the DLC's qualified product list, which means whatever is required, whatever capability that's required to be on the list, the systems and the data produced by the systems, they all have those capabilities.
Thanks, everyone, for that one. And a related question is, to be clear, we have spoken a lot about luminaire level lighting control in this discussion. The DLC definition of LLLC also includes the necessity of control persistence. Can you confirm that this study is focusing on the integrated sensor capability and not focusing on the control persistence requirement as per the DLC definition? Are the utilities requiring both integrated sensors and control persistence for the additional utility rebates referenced in this discussion?
I'll take the utility side, which is if the utility points to the DLC QPL, then it does require the control persistence function to be defined as LLC. Every utility is different in how they approach it. If they're allowing for the NLC side, then the control persistence may not be required, but if they're focused on the LLC side, then the control persistence is required. For, again, my opinion, control persistence to utility is vastly important, because what that basically says is that if the system loses connectivity to one or more of the sensors or one or more of the fixtures, that is not going to revert to an all-on mode. It's going to revert to an energy efficient mode. So in a utility's perspective, control persistence is highly sought after, because we don't want to see these systems not save the energy that we've been, are counting on them savings if they're not connected correctly or there's something going on inside the system. So for a utility side, again, my opinion is that is important enough that they would require it, but every utility is different and every utility has their own requirements. But if it's LLC and pointing to the list, it does have to have the controls persistence.
Thanks, Chris. Yeah, did you want to add anything?
Yeah, the specific answer to the question is yes, because as I mentioned, all the NLCs with LLLCs included in this study, they are all on DLC's NLC QPL, and since control persistence is one of the required capability, so they are all equipped with this particular capability.
Great. We have a couple more questions. Hopefully everyone is able to stay on for the additional 15 minutes that we have scheduled. All right, so in some NLC systems, you have fixture-centric and node-centric topologies, where fixture-centric has the intelligence in each fixture and node-centric relies on sensors being connected to it. With the luminaire level lighting control savings, was the high-end trim control on each individual fixture?
I don't know that we can answer that completely, but with LLC, they are capable of that. As to whether or not they were grouped or zoned to be, one set of HighEnd Trim or each fixture was set up to be its own HighEnd Trim. I don't know that we got that granular of detail. Do you know, Yao? I would imagine we didn't, but or if we did, it wasn't with everybody.
Yeah, so no, we could not answer this question definitively because, like I said, we don't have all the static attribute we need. So for some, we do have the data on how the zones are commissioned and how the luminaires are grouped together, but not for all of them. So we are not sure whether the HighEnd Trim is implemented to a group of luminaires or included blanketly to all the luminaires or individual luminaires.
Thank you both. Okay. I don't see any other questions pouring in. Thank you, everyone. Those were great questions and good discussion. I think we can move on with capping this off.
All right, thanks, Emily. And thank you everyone for joining. This concludes the presentation. And as I said before, the report is already available for download in the website. The webinar will be uploaded sometime next week. Thank you once again.